Okay, so this is an exponential functions overview. This is take 2. This is for data A class here. Alright, so first off, I want you to recognize that there's multiple forms for an exponential function. And example here, the general one, that's the y equals a times b to the x. The compound interest one, you're going to actually see, instead of y, you're going to see a equals p 1 plus or minus r over n and t. Now, the a is actually the same as saying 1, and the t is actually the same as saying, a is y, sorry, and the t is just like x. They're synonymous in your calculator, so just an FYI. So those are your variables there. In the compound interest, just a reminder that n is the number of compounds in a year. So like if it's quarterly, then it'd be 4, and then the interest rate is the decimal. So if it's a 5%, then it'd be like 0.05 on that. Compounded continually, this is called the PERT formula. Again, it's y equals, and it's p, and now e is a number actually. It's a specific base, and it works for compounded continuously. You won't need to know why unless you're taking calculus, and you really don't need to know then, but it shows up why it's e. Again, another method. And then shifted exponentially. Now this one is something that we're not going to spend a whole lot of time with, but it's actually really, I think, good, is looking at any graph that's shifted. So like we have a, your base, it's x minus h, and then it's plus k. This is just like the top one here, this one here, except now, instead of being one that has a horizontal asymptote just at the x-axis, now it's going to have a horizontal asymptote at k, whatever k is. That's the new horizontal asymptote. And this here, x minus h, that means it's going to be shifted right or left. So you're going to be moving a graph. So that's one that I'm not going to plan on doing. It may happen, depending upon the year, but it depends on how many snow days each year. So that's that. All right. So these are the 4 different forms. We have the general one, the compound interest one, compounded continually, and the shifted exponential. All right, here's an example of a compound interest formula that you should be able to do and expect. So compound interest, Paco invests $1,000 into an account compounded monthly. So first off, you need to recognize it's monthly. Write the equation, how much will you have in 4 years, and the interest rate is 7%. So using the compound interest formula, P, which is the initial amount, so let's go back here. So P is the initial amount, this value right here. So, and then 7% is going to go here, and it's monthly, so that's going to be 12 for the N. So it's $1,000. It's compounded monthly, so it's over 12, and 7% is 0.07. And we have the exponent of just simply 12t, so because N is both in the denominator here and also up here, because it's getting compounded every 12 times in a year. Alright, so now at this point you need to go ahead and type it into a calculator if you want to find out how much he has in 4 years. So the exponent, that means if he has 4 years, he's going to compound it 48 times, because 4 times 12, that's how we get that there. So if you type it all into your calculator, and this there, and it's going to be to the 48. Now the caret key is what you use for the calculator here, and the final answer then would be $1,322.05 in this one. So compound interest, this is just a situation. Big thing is that you need to be able to use the monthly, etc. Monthly interest rate's a decimal. This is the initial amount is the number in front of the parenthesis. So those are the big things you need to be able to recognize. All right, now compounded continuously. This is the PERT formula. So y equals p e r t. All right, so so now you can, again, each of these exponentials can actually be manipulated to be in any of these forms, but compounded continuously is the only exponential you'd use in calculus. It's the best one for that, so it's something that we do want to be able to use, and it is easier. So in this one, an isotope is compounded continuously at a rate of 2% loss per year, so it's losing 2% of its value every year. Alright, so I want you to make sure that you notice that that's loss. Write the equation. How much will it be after 1 year if it was originally 10 grams? So it starts at 10 grams, E, which is a number, and since it's losing 2%, it's going to be minus 0.02 T. And so then you just type in with 1 and for this spot here, because we want to know after 1 year. And so if I do this real quick, then it is 9.8019. Okay? Now the next thing is, the better you are with the graphing calculator, the more beneficial it can really be in this. And any of the things that go beyond this, the better you are with your calculator fluency, the classes get easier, the ACT gets easier, that kind of stuff. So first off, graphing on a calculator, if I want to graph this equation, I'd go ahead and hit y equals, which is of course this button right here, and I'm going to type in 200 times 0.75. Now to get the exponent here, now mine shifts it up because it's math type or whatever, pretty type. Yours may not. It may just put a caret. It might just show a caret, so it might look like 200, and it might say times 0.75, which is the same, and then it would go caret. And now the one thing is, if you have more than one thing that goes in the exponent, be extremely cautious. Make sure you have parentheses, but in this case we only have x, so you don't need the parentheses because it's only one thing. But your calculator needs those parentheses, unless of course you have it in pretty type like this one. So if I'm graphing this, now I need to be able to figure out what my window's got to be. This window I need to figure out, and I have to use my brain. Zoom fit, Zoom works great for a lot of things. Zoom fit is not one that works well for exponentials. It zooms too far out. I would not use it. Anyhow, we know a couple of things about this, so this should be helpful when we're choosing a window. We know that the y-intercept is 200, and now the fact that it's 0.75, that means it is decay, all right, because b is less than 1. So if b was greater than 1, we'd have growth. So that means that if I'm looking at a window here, I need at least 200, at least, because it's got to cross at 200. So if I put 200 here, say 300 could be the top of my window on that. So this is what the graph is going to look like here. And this is my window. So I chose -1 to 10. So that's -1 here to 10. And it's going to show a nice exponential curve. If I don't see a nice exponential curve, one of the things that went wrong, like maybe I'm zoomed too close, or I typed it in wrong. I might have forgot the exponent, that kind of stuff. But I chose -10 to 300. Why did I choose a y min less than 1? So that way I could see the x-axis. The x-axis is at 0, and so by choosing -10, I'm able to see the x-axis. Otherwise it wouldn't show up there. See, it crosses here at 200, and it's exponential decay because it's less than 1. Okay? Now, solving on a calculator. Say I wanted this exact same problem, and I don't even know what it stands for, but say I want to know when it's equal to $35. So when does it equal 35? Now, we mentioned in class, if I have 35 equals 200, and it's times 0.75 to the x. I have to guess and check on this entire thing and trying to figure out what this is. The only way to solve it analytically is using logarithms, which we have not done yet. Alright, but there is a way to use it on your calculator. Solving on a calculator, we're going to go ahead and input this into our calculator as y equals, oops, the screen sort of, so I've got y equals here, 35, and the other one, which is of course our original problem. So now once I hit graph here, both of these are going to be in the window. If I graph this and they don't intersect, maybe I don't have the window large enough, then that means I need to increase my x's. But in our case, they will intersect here. We want to know when they intersect, so that's going to be the solution to this. So if I graph this, I've hit graph, I've got both of them there, and it's going to intersect right there. So at this point, now I need to solve it. Well, a graphic calculator is sweet because you can solve any two equations this way. You put one in equation 1 and the other one in equation 2. It doesn't have to be a constant. It could be any two equations, this one and this one. Left-hand side of the equal sign, right-hand side of the equal sign, graph them, and see where they intersect. And once you see where they intersect, then you do second calculate. All right, and the reason why I say second is because calculate's in blue here. Your older calculators, it's in yellow. But so it's blue, and second calculate, and it's number 5, which is intersection. And intersection, it's going to say first curve, second curve, guess, and then it's going to say the answer here. So you just hit enter 3 times, and then eventually it'll tell you that the intersection point is when x is 6.5 or 6.0586, it is equivalent to 35. So if I were to take and plug in into my original problem, which was 200 times 0.75, and use the exponent of 6.058, etc. If I do that, I will get the value of 35, and that's what I was trying to find out. So that beats guessing and checking. So your calculator can be extremely helpful here. Now, table also can help you out significantly. So if we need to, in this case, if we want to figure out and create a table, your calculator, again, can be extremely helpful. So if you hit second table, and I find it very beneficial when you do this to have the table set up so that the independent is at ask, and because it's going to say auto or ask, and I really like it when it's at ask because I can just type in the value that I want. So I typed in 0, I typed in 1, I typed in 2, and I typed in 3, and then it automatically gave me what the y values were. So I can figure out, I can jump, and I don't have to follow the table specifically. So the table is a very, very beneficial way to solve things. Like if I wanted to know, if I wanted to know, well, okay, when is it equal to, say 100? Well, I can see that it's between 2 and 3, that it's equal to 100, and I can do some guessing and checking if I wanted to. But anyhow, the table is extremely helpful. It's a nice way to do that. Okay, just a reminder that exponentials are multiplying, and I strongly think that exponentials are the most beneficial to multiplying pattern, right? And that I think these are the most important ones that we can do in our classes. If you understand exponential functions, it's a huge deal with investments and all that kind of stuff. Some non-calculator questions that you might have to deal with is, say, writing an equation for an exponential. So here's an example of write the equation. We're going to get a different equation than if you did an exponential regression. We're going to get one that's going to be really nice to work with. Now, the first off, do you actually know if this is exponential or not? And that's the reason why I chose this problem. Is there something that we're multiplying by in order to get to 65? And then is that same thing the same value? So b, which is again the base of the exponential, you can figure out by taking the second y value and dividing by the first y value. So 65 divided by 50, if I do that, that is 1.3. And if now to check to see if it's exponential, if 84.5 divided by 65 is also 1.3, and if I type that in my calculator, guess what? Lo and behold, it is 1.3. So that means that after 6, I could go ahead and continue the pattern, times it by 1.3, and I'm going to get the value of 109.85. So yes, it is exponential. Now, if I want to write the equation for this, it is, well, first off, I started at 50. So I started at 50. That's the first thing. I'm multiplying by 1.3. Now, the one thing is, it took me 2 units of time to have this 30% gain. So I'm gaining 30%, but it took 2 units of time. So that's where that x over 2 comes into play. And there's my equation. And so that's my exponential equation for this. Another example would be off of a graph. If you had some graph and you go, oh, look at that, that is exponential. It crosses at 20, and this point here, let's say this is 3 and this is 50, but it definitely looks exponential. So we started at 20, that's the y-intercept, so we recognize that. So how did I get to 50? Well, what is the multiplying factor? Again, I do 50 divided by 20, that's the opposite of course, multiplication, to figure out that that's 2.5. I can't believe I started to type that in my calculator. And my exponent is x over 3. Once again, your calculator will not get that for you if you do a regression. It will use, it would be 20, and then whatever 2.5 is to the 1/3 power to the x. But that's not how your calculator would show you. It would show you it as a decimal. So it'd go 2.5 to the 1/3 power. If I do this correctly on my calculator, it is 1.35 at the base. So 20, 1.35679, etc. to the base. So this and this are identical. They're the same. And it's the same as the one we have above. Well, this one makes a whole lot more sense. So your brain can do a whole lot better than your calculator can in this, in terms of figuring out this equation. Another one, say you have a half-life problem, and it says the half-life is 4 years. Okay, I have no idea, I'm just making up numbers. So half-life is 4 years, and there's initially 100 milligrams of whatever the compound was, isotope was. So the half-life is 4 years. So what's the multiplying factor? If it's half-life, guess what your base of this is? It's 0.5, or 1/2. And the half-life is 4 years, so it's x over 4. And there's your equation. If it's doubling, then the base would be 2. If it's tripling, then the base would be 3. Anyhow, this is just the introductory to exponentials. Hopefully this has been helpful, especially with your graphing calculator. But you know, the big thing is being able to become proficient with your graphing calculator. All right, enjoy.